Hi guys, welcome to the third video for physics. So we've been talking about wave motion in one direction. The next part that we're going to move on to is looking at wave motion in two directions. Now, as part of this video, what I did want to show you is three important points. So wave fronts, so what that is, as well as Huygens principle and what that means for wave fronts. I also wanted to talk about reflection, and I want to start talking about refraction. Now, I know in the video we saw today, they also talked about diffraction and the single and double slits. We're going to get onto that a little bit later. Okay, so the first thing to talk about, okay, so what is a wavefront? Okay, so a wavefront, the easiest one to see is the water waves. So obviously we talk about light waves and sound waves a lot, but the ones we can actually visualize are our water waves. And when we have a look at, say, a water wave, there's a couple of ways of actually visualizing it, okay? So you can start off with, as we often see, we have one drop in the center of a pond or something like that, okay? And as you know, it radiates outwards, okay? And you actually see this ripple going outwards. Now, what these ripples actually are, that's actually the crest of the wave. And the distance between these crests, okay, is lambda. Okay, so that's equivalent to the wavelength. Another word for crest when we're actually looking at these waves is wavefront. So that's actually the wavefront that we're actually looking at. Now, the other type of one that we can look at, we haven't seen this yet, is a straight wave generator. So what you do is you have your straight wave generator like that. Okay, and so that actually generates waves going outwards, and they go in a straight line. Okay, and they continue outwards like that. Again, the distance between these crests, or between these wave fronts, is equivalent to lambda, or one wavelength. Okay, that's the direction of propagation in this sense. This one, direction of propagation goes out in all directions. Okay. Now, it's often difficult to measure the actual wavelength of these waves because they are continually moving. You can use a whole lot of different types of instruments to actually measure it. So one is the stroboscopes. Hopefully we'll get to use some of these instruments in the next little while. Okay. Now, Huygens principle is the next thing that I wanted to talk about. It's actually not a difficult concept for you guys to understand. So when you see, say if we're looking at our drop here, we're having a wave front like that. So it's the crest that comes outward. What he actually proposed is that each individual point on this then creates its own little mini wave front, okay? And with each of these, okay, and every single point along the wavefront creating a new little wavefront, kind of ends up looking like that. Okay, and then what that does, it actually creates a new wavefront coming along here. So you have the continuation of the wavefront. Okay, not a hard one at all. We're going to work on some questions related to that in class. The next section that I wanted to have a look at is reflection. So most of you are quite familiar with reflection anyway. Okay, so that one's there. So if we're, say, looking at a wave, we'll call it, EFG, okay? So it's coming along here. So we're making that EFG, okay? For the purposes of this, we'll look at it this time as a straight one. So it's getting generated from over here, okay? And so it's continuing on and on and on, okay? When it actually hits, when the new wavelength actually hits, it gets reflected back perpendicularly. So if you're looking at a barrier here, okay, something it hits, I'm trying to make that flat, but I'm not really succeeding. Okay, so if this hits at this angle, okay, it's also going to get reflected back at that same angle, okay? So it's an angle with the normal, okay? So what we're actually doing is the normal is absolutely perpendicular, okay, to the object that it's actually hitting, to the barrier it's hitting, Okay, so if that's, say, oh gosh, what does that look like? 45 degrees. This is also going to get reflected back at 45 degrees. Same as this one, okay? If it goes along and hits at, okay, say 50 degrees, it's going to be reflected back at 50 degrees, okay? And so on, okay? They all get reflected back at the same angle to the normal, okay? Then what actually happens is they then interact with each other. So this one hits here, it interacts with this wave as well, okay? And it produces those areas that we saw in the video. So some areas with antinodes and some areas with nodes. Okay, we can go through that in a little bit more detail anyway, okay? So basically, the principle there that we do need to remember, and I'll write it down for you because it's very important. Angle of incidence equals the angle of reflection. So the angle of incidence is where it actually hits, okay? That's where it starts, equals the angle that it gets reflected back on. Again, remember it's to the normal. So if that's your wave and it's hitting like that, okay, that's the normal, okay, because you've got your barrier here. That's the normal, and it gets reflected back at that same angle, okay? So we'll say that's angle A. That again would be angle A, okay, and it gets reflected back up that way, okay? So not a difficult concept, hopefully. The next one that I wanted to talk to you about is refraction, okay? Refraction. We have started to talk about that. So we talked about transmission, okay, and so we were looking at two different mediums. So going from a lighter, less dense medium to a more dense medium, okay. What can happen is refraction, and that was also in that video where we saw the pencil. So you saw the pencil under the water, and it looked like it was slightly bent, okay. So that's the kind of thing. Missed out on my awesome drawing. Okay, so it kind of looked like that. Okay, now when they go from one medium to another, obviously these properties change. Okay, so for water waves, simplest thing you can do is actually change the depth. So again, if we use say our ripple tank for example, okay, so you've got a tank that looks like this. If we built this up here to make this more shallow, okay, so if we're showing the waves that, say if we use a straight wave generator, okay, they're creating waves like this. If it goes to somewhere that's more shallow, the properties change. Now, as you can hopefully see there, the shallower water, okay, tends to be, you know, a smaller waves there. Okay, so we tend to remember with the 3 S's. So the shallower, in shallow water, it's short and slow. Okay, so let's explain a little bit how that actually works. Okay, so waves travel more slowly in shallow water compared with deep water. Okay, the frequency stays the same. Okay, so remember, what is frequency? Frequency is how many waves or how many crests pass the initial starting point per second, okay? How many cycles are going out per second? Now, in this case, it's staying the same, okay? The ripples are still getting sent out, the waves are still getting sent out. So the frequency stays the same, okay? I'll write that down for you. Frequency stays the same. However, okay, the speed actually slows down, okay? So V actually becomes less. It gets a little bit slower, okay? So V, or speed, velocity, whatever you'd like to call it, okay, slows down. Now, knowing what you guys know, and you know the formula that we're actually going to use, okay, V equals F lambda. Okay, if we're saying that the frequency stays the same, but V gets slower, what do you think happens to the wavelength? Have a think about it, I'll let you think. okay? Obviously, this must also decrease, okay? Because this is staying the same, this is getting less, this one must decrease as well, okay? Otherwise, it wouldn't, the formula wouldn't work. Okay, so you have to remember that one there. So what's actually happening in shallow water? Gets shorter, okay? The wavelength decreases. The speed decreases. Frequency stays the same. Okay, so they do say the 3 S's: shallow, short, slow. Okay, whereas with the deeper water we have the depth is deeper, okay, the wavelength is longer, the speed is faster. Okay, now with refraction, okay, so we haven't really talked about it too much in class yet. The angle of refraction and angle of incidence, as you remember when we were talking just before about reflection, refraction is actually a little bit different, okay? So it's okay. Sorry guys, the sound just blanked out there for a second. Okay, so we've still got our angle of incidence, okay, hitting our wall here. Okay, except it actually does change just a little bit when going from deep to shallow water. The angle of refraction is actually smaller . Okay, is smaller than angle of incidence. That's when you're going from deep to shallow. Okay, so the next S that they tell you to add to the list after that is small. Okay, so the shallow water is small, short, and slow. Okay, so those are the only things that we really want to do. What I would like for you to do is have a look at question 9 on page 292. Okay, and attempt question 10 as well if you can. Okay, so those questions, and we'll have a look at them tomorrow. I know I've gone through this stuff quite quickly and we are going to go over it again tomorrow. It's just to start you off, get you started with it. Okay, see you guys tomorrow.